Okay, all right. Okay, first of all, I would like to thank the organizers for organizing this workshop and for inviting me to give talk on my recent work. I'd also like to thank all the listeners who have taken time out of their busy schedule to listen to it. I hope all of you and your family members are staying well during this pandemic. So I'll be talking about detecting ultralight primordial black holes as the dark matter candidate. These works have been done in collaboration with these collaborators, wonderful collaborators. So what do I mean by ultralight primordial black holes? How do I define it? So in this talk, I'll be talking about black holes in the mass range of roughly between 10 power 15 grams to 10 power 19 grams. That's the definition of ultralight primordial black holes in this talk. So the way I'll structure my talk is that first I will be talking about some recent papers which motivated the fact that ultralight primordial black holes can make up 100% of the dark matter density. I'll then move on to my own work where I showed that in this parameter space, measurement of galactic center positrons and galactic center photons can constrain the abundance of ultralight primordial black holes. I'll then talk about how proposed telescopes can also probe large parts of the parameter space of ultralight primordial black holes before concluding. All right, primordial black hole. So in this slide, I'll be talking about some recent papers which motivated the fact that ultralight primordial black holes can make up 100% of the dark matter density. So these are the papers by Katz et al., Montero Camacho et al., Inamata et al., Smith et al., and this Subaru measurement. So what is this plot? Let me go through this slowly. So on the x-axis, what is being plotted is the primordial black hole mass. And on the y-axis, what is being plotted is the fraction of dark matter in the form of primordial black holes. All right, so obviously the fraction is bounded by 1. Anything that is shaded in this plot, that means this region, these regions are ruled out due to measurements. For example, this region is ruled out due to observation of extragalactic gamma ray background. These regions are ruled out due to lensing. This ultra-faint dwarf region is ruled out due to dwarf galaxy dynamics. The CMB region is ruled out due to observation of the CMB photons. But earlier, before 2018, before the appearance of this paper, there was a region here which ruled out primordial black holes in this mass range due to femtolensing of GRBs. What Katz et al. Showed is that that paper was overly optimistic in the sense that they did not take into account wave effects and the finite source size effects properly. And once you take that into account, this constraint goes away. So these lines, these blue lines, are basically their future projected limits. So there's no limit here. This white dwarf thing, this was another paper which earlier showed that primordial black holes moving through white dwarfs can destroy the white dwarfs. However, it was shown by Montero Camacho et al. In using simulations that this is also probably overly optimistic, and this is also ruled out. And then this Subaru HSC, we already had talks on this. It was pointed out by Inamata et al. And Smith et al. That this has to be modified. Right. So overall, in the end, what we learned from all of these papers is that there is a parameter space where primordial black holes can have a mass from few times 10 power 16 grams to 10 power 23 grams, where they can be 100% of the dark matter density. Note that this is not the most updated plot, all right, and this doesn't contain all the constraints. So you may want to look at these papers for the most up-to-date constraints. So when I started to think about this, I started to think, how can I probe ultralight primordial black holes, especially in this mass range, from few times 10 power 16 grams, say to 10 power 18, 19 grams? Is there a way to probe it? Typically, at these very low masses, primordial black holes are constrained by the presence of the Hawking evaporation. So let me give you a brief overview of Hawking evaporation. This is a celebrated results by Hawking, and you can also look at this paper for the history, that black holes, every black hole has a temperature associated with it. So if the black hole mass is MBH, the temperature is TBH, and a 10 power 10 kilogram black hole has a mass of 1 GeV. All right. One can also calculate the energy spectrum of particles that are being emitted from black holes. So this is given by this expression, where E is the total energy of the particles and S is the spin of the particle being emitted. This part, as you can see, is sort of like a black body radiation, except that there is a gray body factor, which tells you how much is this whole full expression different from a black body radiation. This expression, this factor, depends on the mass of the black hole, the spin of the black hole, the total energy of the particles being emitted, and the rest mass of the particle being emitted. Again, you can look at these papers for references. So how does this spectrum look like? So let me show you this plot from this paper by McGibbon and Weber. Note that here I have slightly changed the notation just to give credit to the original authors. Here Q is the total energy of the particle. All right. So what is being plotted on the x-axis is the total energy of the particles times the mass of the black hole, and the y-axis is the differential spectrum per unit energy per unit time. All right. So for an uncharged, non-rotating black hole, if it emits pions, the spectrum looks like this S equal to 0 line. All right. If it emits E plus E minus, the spectrum looks like this S equal to 1/2 line. And if it emits photons, the spectrum looks like this S equal to 1 line. And these authors also plotted a representative black body spectrum to show that there's actually, this is not really a black body, there's some difference. It closely resembles a black body. From this plot, you can also figure out the energy at which all of these fluxes peak. Say, for example, if you have spin 0 particle, the peak is roughly at 2.8 times the temperature of the black hole. For spin half, it's 4 times the temperature of the black hole. And for spin 1 particles, it's 5.77 times the temperature of the black hole. So that means if you have a black hole of mass BH, you can calculate the temperature TBH, and you can figure out the energy range in which its emission, particle emission, will peak, depending on the spin of the particle. All right. So what did this parameter space for ultralight primordial black holes look like before I started to think about this thing? Again, what is being plotted on the x-axis is the fraction of dark matter, on the y-axis is the fraction of dark matter in the form of PBHs. On the x-axis is the mass of the primordial black hole. So the story in all of these cases is as follows. Primordial black holes evaporate, produce various kinds of particles, and these particles should not overproduce the observed flux that we measure astrophysically of photons, electrons, positrons, and many other particles. So this black line that you see is a result from this Carr et al., which showed that if primordial black holes exist and they emit photons, then at a density above these lines, above this line, that means this is an upper limit, is ruled out from the measurement of the extragalactic background and the gamma ray galactic background. All right. It was also shown in this paper by Boudat and Shirelli that if primordial black holes again exist in this mass range, they will also produce E plus E minus, and then they can be constrained by the measurement of the E plus E minus by Voyager. Right. So Voyager is a satellite which is now beyond the heliopause, and it can measure E plus E minus, low energy E plus E minus, and depending on the propagation parameters and the background consideration, the constraints are this red lines, red and blue lines, dotted and solid, right? Again, these are upper limits, so anything above is ruled out, right? This line is the GIB femtolensing limit, which was earlier showed by, which I earlier mentioned, showed by Katz et al. That this is ineffective. So I started to think, can you probe primordial black holes in this mass range from a few times 10 × 16 gram onwards? Is there a way to probe it using Hawking radiation or any other methods? That answer is yes. So the first thing that I came up with is constraining primordial black holes from the measurement of the Galactic Center 511 kV gamma ray line. You can find the journal reference and the archive number in this in the archive number here. So let me first give you a brief explanation of what is INTEGRAL. So INTEGRAL stands for International Gamma Ray Astrophysics Laboratory. This was a satellite launched by ESA in 2002, and it has made some great progress about gamma ray astrophysics. It has made the best measurements of the 511 kV gamma ray line in the Galactic Center. It has given insights into galactic nucleosynthesis. It has given insights into dark matter studies. It has given insights into pulsar studies, even insights into multi-wavelength studies, many different things. It's a great satellite, great, highly successful satellite. It's still working. So there are many instruments on INTEGRAL. The instrument that I will be talking about is called Spectrometer of Integrals, SPI. It has an energy range of roughly 18 kV to 8 MeV, and it has a superb energy resolution at these energies. This can go less than 1%. Right? So now let me tell you an astrophysics mystery, a 50-year-old astrophysics mystery, which we still have not been able to solve. It's a fascinating mystery. So if you have a gamma ray telescope, which can observe 511 kV gamma ray line, and you look at the galactic center, this is how the sky will look at it, right? So there's a map. So this is the galactic center. This is the galactic disk. This is the galactic bulge, right? You see a bright flux of 511 kV photons. So this is the brightness. You see the brightness goes from red to blue, and then black means there's no brightness, right? You see a bright flux of 511 kV photons. This has been measured by various different instruments. First started measured by Johnson et al. In 1972, and it has been still going on. Even this year, people have measured it. So this is a almost 50-year-old measurement, right? This has been measured by various instruments, so we know it's not systematic. It is actually real. So the question is, what is the source of this radiation? We don't know the answer, even after observing these photons for 50 years. However, we do know that these photons are being produced by E plus E minus annihilation at semi-relativistic speeds. For example, you can measure the monochromatic photon line, that means the 511 keV line, and the photons at slightly lower energies to estimate the positronium fraction, which is almost close to 1, right? So this means positrons are being emitted in the galactic center, they lose energy, they slow down, they almost come to rest, they get captured by electrons, they form a positronium, and then they decay, right? So this is the main thing. You can actually also constrain the injection energy of the positrons by looking at higher energies, right? And this was done by these papers. So in this two plots, what is being plotted on the y-axis is the flux, and the x-axis is the energy of the photons. So this is the spectrum in the bulge, this is the spectrum in the disk. So as you can see, both of them show bright 511 keV photons, and there is a continuum spectrum, as you can see here. And these are the various fit parameters. So as I said, from these flux measurements, we actually know that in the bulge, the positron injection rate is 2 times 10 power 43 per second. Right? This is known very precisely. And although we do not know what is producing it, there are multiple models in the literature. It can come from millisecond pulsars, low mass X-ray binaries, neutron star mergers, supernova, stars, maybe even dark matter. But none of them have been confirmed to give rise to this entire emission. None of them can, at least till now, we have not confirmed which can give rise to emission in the bulge and in the disk. It's an ongoing mystery, and there are even proposed telescopes to solve this mystery. So the question that I asked, can we derive a robust constraint on primordial black holes using this observation? I must tell you that I'm not the first one to think about this. This has been thought about by many people even before I was born. So the first paper, as far as I know, is by O'Kelly and Rees in 1980s. Okeke wrote it in 1980s. Magiban and Carr wrote it in 1991, and Bambi, Dolgov, and Petrov wrote it in 2008. So even though we do not know what is producing these 511 keV photons, what we can robustly say is as follows. If there is any source which is injecting positrons, it cannot inject more positrons than 2 times 10 power 43 per second. Otherwise, it will violate the measurement. Right? Remember, that is the injection luminosity of positrons. So we can try to calculate this by using this simple formula. This is again the spectrum of positrons per unit time per unit energy. You integrate over the relevant energy range. This expression gives you the total number of primordial black holes in your field of view. So this is the dark matter halo density. This is the mass of the primordial black hole. This is the volume. And then you multiply by the fraction of dark matter in the form of primordial black holes. And you simply want that this expression must be less than 2 times 10 power 43. And from this, if you know all of these, you can find FDM. Right? That's the limit. Note that if you are familiar, this formula mimics decaying dark matter. So many primordial black hole formulas, evaporation formulas, mimic decaying dark matter. However, there are many uncertainties. For example, we do not know positron propagation in the galactic center. That's a big uncertainty. We do not know the dark matter density profile in the galactic center. That's also a big uncertainty. And these I'll show it in my results. So again, what is the story? Primordial black holes of appropriate mass will evaporate to produce E plus E minus pairs. These positrons will lose energy, become non-relativistic, and will annihilate first of all, will produce a bound state and then annihilate to produce photons. And then these photons are what is being observed by integral, or what can be observed by integral. So what is being plotted here on the y-axis is again the fraction of primordial black holes in the form of fraction of dark matter in the form of primordial black holes. On the y-axis is the mass of the primordial black hole. These red dotted lines that you can see are the various lines. These are upper limits which show that primordial black hole fraction cannot be greater than this number. So anything above these red dotted lines is ruled out. So my constraints are shown by these black lines, this black dash and the black solid line. So let me tell you what do these stand for. As I said, due to the uncertain nature of the dark matter profile in the galactic center, there's this uncertainty. So if the dark matter profile is isothermal, the constraints are typically weak. If the dark matter profile is NFW, the constraints are typically strong. The other uncertainty is due to positron propagation. What we do not know, if a positron is produced at the galactic center, how long, or what is the distance it travels before annihilating? Does it travel 100 parsecs from its production point? If it travels 100 parsecs, then it is this line, this IISER 1.5 kiloparsec and NFW 1.5 kiloparsec, all right? So this 1.5 kiloparsec tells you what is the volume, what is the region over which you do the volume integral in the previous slide that I told you. However, there are also scenarios where the positron can travel 1 kiloparsec from its production point to annihilation point. Then you have these things, right? IISER 3 kiloparsec and NFW 3 kiloparsec. Again, this 3 kiloparsec tells you the volume over which we do the integral in the previous integration in the previous slide. Note that these constraints are for the monochromatic mass function, that means this delta function, and whatever you take, you still beat all of these limits. All right. I would also like to say that during the same time as my work, there was this paper by William D. Rocco and Peter Graham who came to the same conclusion. It was published simultaneously. So the previous plot was for non-rotating primordial black holes with a monochromatic mass function. You can also do it for extended mass function. Again, I took two kinds of things. One was the log normal mass distribution. This is the d-phi dm, where the parameters are mu and sigma. Again, what you plot on the y-axis is the fraction of the dark matter in the form of primordial black holes. Mu is the parameter on the x-axis. These dotted lines that you can see, sigma, are coming from the Voyager measurement for various sigmas. Again, these are upper limits, so anything above these lines are ruled out. My constraints are these black lines, all right? Sigma equal to 0.1, sigma equal to 0.5, sigma equal to 1, and sigma equal to 2. So these are the bands, right? So this is the weakest constraint, most conservative constraint, as I showed in the previous one. This is the most strongest constraint, depending on the dark matter density profile and the positron propagation distance. One can also do the same thing for power law mass function. This is parameterized by this expression where gamma is the spectral index, M max and M min are two parameters, and you get very strong constraints. So whatever I do find that the constraint from the observation of 511 keV gamma ray line at the galactic center provides some of the most stringent constraints on ultralight primordial black holes with extended mass function. All right. So after doing this, again, this is for non-spinning primordial black holes. There's a very simple question you can ask: what happens if primordial black holes are spinning? There are various scenarios which can produce this, and this was again done in this paper. You can find the reference, archive number, the journal reference. So for spinning primordial black holes, what we can do is, suppose the angular momentum of the primordial black hole is defined as J, then we can derive this. We can define this reduced spin parameter J by Gn mbh squared, right? And this A star can take various values from 0, that means it's non-rotating, to almost tending to 1, that means it's maximally rotating. And this factor changes the PBH, temperature of the black hole, right? So remember the previous formula is modified by the presence of this factor, right? This fraction. So now you can do this, take this expression and then try to calculate the Hawking radiation spectrum and try to compare with measurements. Again, what is being plotted here in this plot is the y-axis is the fraction of primordial black holes, which is in dark matter, which is in primordial black holes, and the x-axis is the primordial black hole mass. These orange lines that you see, the shades of oranges, are coming from gamma rays. All right, this dotted line is for non-spinning, this solid line is for almost maximally spinning. And these lines are our constraints. All right, these shades of blue, various shades of blue are our constraints. So again, you can see this the galactic center 511 keV line can give you new constraints with the parts of parameter space which was not constrained even for spinning black holes. This was for monochromatic mass function. You can do the same thing for log normal mass function. Again, the y-axis is this fraction, the x-axis is the mu PBH. Again, you see these shades of orange are the gamma ray constraints, and the shades of blue are the galactic center positron constraints. And you can see there's a very nice interplay between how they change depending on what mass range you look at. In all cases, again, you do see that the galactic center 511 keV line do probe new parts of the parameter space, which is not probable by any other means previously. All right, after doing this, I started to think, is there any other way to probe? Is there a way to even do better? So this was done in this paper with these collaborators. Again, the archive reference is given here. The journal reference is given here. So before doing this, you need to understand, you need to ask a simple question, try to think how it is solved. How do we know the cosmic ray electrons and positrons at the galactic center? Again, we can't directly measure it, right? So the only indirect way to measure cosmic ray electrons and positrons at the galactic center is to measure their energy loss. And this has been done by various different instruments, especially integral, where integral measures the gamma ray spectrum at the galactic center, at the galactic bulge, the galactic disk.
We have 5 more minutes.
Yes,
5 more minutes.
Yes, thank you. Disk, and it tries to compare it with theoretical models of cosmic ray electrons and positrons. And using this, you can probe cosmic ray electrons and positrons at energies less than 5 GeV, roughly 5 GeV. So this is the integral measurements, these two. So now let me go through this slowly. What is being plotted in the y-axis is the flux per steradian for all of these things. Let me first explain just this part, right? Flux per steradians. On the x-axis is the longitude, right? All of these plots. For these four plots, the data is integrated over this latitude range from minus 6.5 degree to plus 6.5 degree. For various energy bands, 27 to 49 kV, 49 to 90 kV, 100 to 200 kV, 200 to 600 kV. And in this, for this, at this energy range from 600 to 1800 kV, they integrate it over this wider latitude range from minus 8.2 degree to plus 8.2 degree. These crosses that you see in various different things are the data points, right? And these blue line, the red line, and all of these things are the various contributions of the diffuse gamma ray spectrum at the galactic center. All right. You can do the same thing where you integrate over a longitude range minus 23.1 to plus 23.1, minus 60 to plus 60 degree, and plot it against latitude. All right. Again, for the same energy intervals. Again, you see these are the data points, and there are various. You can explain these data. So overall, what the authors found out, the Boucher et al. Found out, is that there is a good description of the data in the terms of inverse component emission of electrons and positrons, stellar emission, and the annihilation radiation that I talked about earlier. Now we try to use this data set to constrain primordial black holes. Note that this is actually quite difficult because the way they have extracted this data set, it requires a background template to extract these photon energy data points, these and these, all of these things. So what we did is the simplest thing possible. We try to say that whatever happens, the primordial black hole signal cannot overproduce these data sets by more than 2 times the error bar, all right, all these data points. So you take the primordial black hole spectrum, you plot it as a function of longitude for latitudes for all of these things for various energies, and you try to constrain it. Note that this is the most conservative option possible. You can do a better job of modeling the astrophysical backgrounds due to emission of galactic E plus E minus, stellar emission, annihilation radiation, and you get much stronger constraints. But again, our constraints are the most robust constraints that's there, and it's still extremely strong. So what is the result of our analysis? Again, what is being plotted here is the same plots, FPBH versus the mass of the primordial black hole. These Voyager 1, CMB, extragalactic gamma rays, these are the older limits. Anything above these lines are ruled out. The 511 keV was my constraint, but this was the weakest limit. But there was a band here. Here I have taken the weakest constraint in this case. Again, anything above this line is ruled out. Using this integral data that I showed earlier, we can get this line, this black integral, this line. All right, this line is ruled out. There's some using something which is using an older Boucher et al. Analysis. However, that is not robust, so you can just ignore this. All right. So the constraint is basically like this. Again, this is for a monochromatic mass function, and the primordial black holes are non-rotating. The good thing about this constraint is that this is relatively insensitive to the dark matter profile, and obviously there's no propagation uncertainty. You can also try to do this for extended mass functions and spinning primordial black holes, and you find that this is equally constraining, this data set. Recently, I must say that there was also this paper by Koushik et al., which showed that computational limits can also be, computational measurement data can also be used to derive similar limits. All right, so I've come to the last part of my talk. Can we do even better? Is there a way to probe even higher primordial black hole masses using Hawking radiation? So this was sort of, we put out this no mass thing with my collaborators. And this is a work in progress. And what we find is if there's future telescopes or proposed telescopes like Amigo get funded, and if they look at the galactic center, say for 1 year in this energy range from 0.15 MeV to 40 MeV, then they'll get this limit, all right? Again, this is the FPBH on the y-axis, mass of the primordial black hole in the x-axis. All of these lines are the older limits. For non-spinning primordial black holes, this is the line. Anything above is ruled out. For maximally spinning primordial black hole, this is the line. Anything above is ruled out. This is for a monochromatic mass function. You can also do it for the log normal mass function for a specific sigma. Again, you see there are new parts of the parameter space which we can probe, which one cannot probe using any other means. So for non-spinning black holes, for non-spinning primordial black holes, we can constrain our masses up to 8 times 10 power 17 grams. So this is the interpretation, and to look out for the paper. Again, I must say that there's also a similar paper on this topic by Raghavan et al., which tried to study the same thing for various different telescopes. Okay, so I come to the conclusion of my talk. So I try to motivate that ultralight primordial black holes can make up 100% of the dark matter density. Galactic center positrons and gamma rays can be used to constrain or discover ultralight primordial black holes. And there are proposed telescopes like AMIGO, which can probe ultralight primordial black holes in a large region of the parameter space, which cannot yet be probed by any other means. Thank you.
So we have questions, and Swagat, can you please unmute your mic and ask the question?
Hi, I was actually asking about hard X-rays, but I think in the last slide, I think you showed sort of what would happen. So you can push it as down as 150 keV, right? Is this your claim?
Yeah. So the point is as follows. So remember, primordial black holes are actually emitting all kinds of photons and all kinds of particles, right?
Yeah.
But the flux is falling. It's like decaying dark matter. The lifetime of primordial black hole or any black hole is equal as 1/m cubed. That's the killer.
Yeah.
So you can, for example, when I actually started to do this integral work, I was this one. I was very excited. And I tried to look at various. You can do the optical, radio, and you can go completely crazy. And this is what I did. Turns out the flux is super low.
Yeah.
It doesn't work.
From soft X-ray, it's very low.
Yes, from soft. You can even go to even sort of like hard X-ray new star. We tried that. Even new star is not working. So this is super difficult. This is more difficult than I would say even particle dark matter. It's super difficult to find good measurement. I mean, taking any observation, astrophysical observation does not give you a good limit. By good limit, I mean your PBH must be less than 1. You don't always get that. You have to do this very precisely. And there are only very few observations which can do this. So that's why I think it's exciting.
I see. Thank you very much. Yeah.
Thank you. Thank you for the question.
Next question is Patrick Dasgupta. Please, Patrick, please unmute your mic and ask the question.
Yeah, am I audible?
Yes, you're audible.
Yeah, so over last 50 years,
yes,
511 kV line has been seen.
Yes.
Does it have fluctuation over certain time scale?
Yes, so this is a very good question. So yes, so it turns out the answer is no. It's a steady flux over last 50 years. Actually, historically, there were some fluctuations. People saw it in time, but now we know that this cannot happen because so the fluctuations, the initial fluctuation was seen by balloon-based experiments, but with satellite-based experiments, we see no fluctuations. Integral sees no fluctuations. So there's a steady flux. So there's a steady injection of positrons at the galactic center. What is injecting the positrons? Definitely stellar emissions. Stars produce radioactive nuclei. They produce positrons. Definitely, that is definitely one of the answers. But that does not explain the full excess and does not explain the morphology. It's very difficult to explain the morphology. So yeah, again, we don't know the answer. I mean, as I said, people are still trying to build experiments to try to solve this. This is a fascinating astrophysics problem. But yeah.
Thanks. Thanks.
Thank you very much for the question.
Yeah, we have time for one more question. There's no question on the chat, so please unmute your mic and ask the question. All right, there are no further questions, then let's move to the next speaker.